So I put standard deviation in a separate video because it's probably something that's brand new to most of us. So standard deviation is a way of numerically measuring how spread out the data is or how concentrated the data is around a measure of central tendency. Usually what we're talking about is the average. And so you could have a low standard deviation. That means that it's really clustered data. It's really tight around the average. It doesn't deviate very much. Or you could have high standard deviation. You have a big spread of the data. And that means that it's really spread out. And so measuring standard deviation gives us a sense. It describes the data in a numerical way, and we're going to practice calculating these. Now, it is sometimes called the dispersal. That's another word that gets used to describe. So it's a measure of the spread or the dispersal of the data. Typically, it's represented by a Greek letter this time, sigma. And sigma is typed like this, but actually it's kind of like a scripty S, if you will. And so it kind of like an S that closes up on the tail. So this would be standard deviation. Represented by the variable sigma. And to calculate standard deviation, this is the equation. Now this equation takes a little bit of making sense of. And so in these ones, there's a whole lot more letters. This number, or this here, is a weird symbol, and it really just means the total of or sum. Okay, so you add a bunch of things together. What you're adding together is how far each data point is different than the average. So mu is our average or our mean, right? Those are the same things. And we don't need to worry about this being a positive or a negative because we have this squared here. And so this gets rid of any negatives that might happen. Now, n is the number in the sample. So kind of like you were dividing by the number in the sample to get the average, that's a similarity in calculating the standard deviation. So it's the number in the sample. So if it was 6 in the sample or 8 in the sample or what have you, we're going to try to round all of our standard deviations to 2 decimal places. That's what the answer keys will be, unless there's a weird one that is otherwise noted. We're going to try and standardize this. I had a really hard time in this unit having, standard rules on where we were going to end our numbers. And so I've tried to add those in. So we've got an example here that helps us use this equation. And so you can look back to that equation. I like breaking it up into a chart. And so we have an example where we're given a bunch of data, and we want to figure out how spread out this data as a numerical measure. So the first thing we need to do is calculate the average of the data. So this is showing us the average calculation. The next thing we're going to do is figure out how far each data point is from this average. Now, I like summarizing this in a chart. So I put a little chart in our notes here. I'm going to list the data down the side. The chart makes it just a little easier to kind of do this stepwise rather than putting it all into a giant equation here, all in one fell swoop. I do think that breaking it up into the chart makes it a little bit easier to figure out what's going on. So this column right here, what I'm going to do is figure out how far each of my data points are from my average. So x is my 16.3 and mu is the 16.4. So the difference between those two, you can do it on your calculator, is a negative 0.1. I'm going to put the negatives in here, but we're going to see in the next step, it really doesn't matter. The next step is to take that column and square it, which, like I said in the equation, is going to get rid of any of those negative numbers. So if I go down the list here, 16.5 is a difference of a positive 0.1. got a negative 0.3 difference, and all I'm doing is taking the data and subtracting the average value. That's what this line is telling me to do, right? That's why I did that in the chart. And the last one is 0.3. The next thing I'm going to do is take and square the data, or square the last column that I had. And so squaring these, again, I did it on my calculator. The next thing is to figure out the total, or the sum, or that funky symbol that looks like a really pokey backwards 3. So this is the sum. So we simply add up all these numbers, and I'm going to write that number here. So I've got 0.2. So on my calculator, what I do is take the square root. That was something in the original formula I didn't mention. I'm going to take the number that I added up in my chart, so 0.2, and I'm going to divide it by the number in my sample, which is 4. And this on my calculator is something that is much easier to do than the entire formula. And so when I do this, I get a final answer of 0.2236 on my calculator, or rounding it to 2 decimal places gives me my standard deviation of 0.22. These ones take a little bit of practice. I do think that the chart is a sanity saver. What I put the box, the orange box around there is really what I do on my calculator. So the next example gives us a series of measurements, and we want to calculate the standard deviation. So the first thing I'm going to do is calculate the average. I'm going to total the data on my calculator and divide it by 5. And rather than writing out all the data, I have to punch it into my calculator. It should be fine. I'm going to round my answer to the nearest hundredth. In this one, the average works out to exactly 21.6. So this is my mu value. This is my mean. This is my average. In calculating the standard deviation, I do it chart-wise, where I take each data and subtract it and subtract the mean from it. Now, in the notes here, I'm going to keep track of the negatives, but like I keep saying, it doesn't really matter, because the next thing we're going to do is take that value and square it. And squaring it gets rid of any of those negative numbers. So each one, 21.63 minus my 21.6 gives me 0.03. Going down, oh, that's right on the mean. I get a negative 0.01 when I subtract 21.95, or sorry, this minus the 21.6. Moving on down, it's hard to say all these numbers. Hopefully you are calculating them as we go, right? I'm just following my chart system here. And if you want to make your chart pretty, I have a hard time drawing vertical lines. There we go. The next thing I'm going to do is square each of these numbers. So I had a nice stopping point, and I can do this in a separate step on my calculator, squaring each of these numbers as we go. You can see here it gets rid of the negatives. What I do now is total this. So the sum of all of these numbers gives me 0.0014. So looking back to that original calculation, I've done everything because sigma was equal to the square root of the sum of x minus mu squared, right, divided by the number. And so just thinking back to that original equation, hopefully we're breaking it up, but you're still seeing what we're doing. So sigma, or the standard deviation, is going to equal the square root of my 0.0014, right? I did all of this top part, all of this in this calculation. That, I think, is the hard part of this to do. So that's why I do it in the chart. And I'm going to divide it by 5. And so this on my calculator, I'd hit 0.0014 divided by 5, and then take the square root of it. Like I said, our standard deviations are going to be to 2 decimal places, so I get a standard deviation of this, not a whole lot, these numbers are pretty close together, 0.02. So basically, on average, any of the data is only 0.02 spots away from my average. That's a pretty tight data set, a low standard deviation. So the last one down here, if I were to do all the math, and this one is one that works out a little bit awkwardly, so I put it in the notes to talk through. I'm going to take the time to talk all the way through this one. The first thing I'm going to do is figure out the average. I would take all of these numbers, add them together. These were smaller numbers, so I chose to write it out this time. Divide by however many I have. And this one awkwardly comes out to a number that goes on forever. So this 5.666. And I'm going to round it to 7. So you could keep it in your calculator, but I'm going to carry 4 decimals if needed. Right? So most of the examples work out quite nice and neatly. This one does not. And so this one I left in the notes here, and I'm going to show you all the way through because it's a bit of an anomaly that it's got a lot of decimals in it. So I like doing most of the calculations chart-wise. So I list the data down the side. I start by figuring out how far each of the data points are from that average. And so I did this on my calculator. I take 5 minus 5.6667, and just bear with me as I copy these into the video here. Gets a little tedious. These kind of ones maybe are better if you do it more in your calculator, but I do find that it's nice to break it up chart-wise and do it step by step. If you become a statistician, you can come back and tell us that this was a waste of time, but I really think that this is a good way to kind of start it. So the next thing we do is square these differences from the mean, and I'm writing it again to the 4 decimals. Oops. All I have to do is copy. I did this on my calculator already. Almost there. And so what we're supposed to do now is total those deviations from the average. And so the sum of these, I could do it on my calculator. The average, or the sum here, is 33.3349. And having done all of that work, this allows me to calculate my standard deviation as the square root of this big, laborious number that I generated, right, divided by the fact that I have 6 numbers in my sample. And again, I'm really taking the chart to do the work of this number that's up here on the top of my formula. So now on my calculator, I can calculate my standard deviation to 2 decimal places. So sigma equals 2.36. The standard deviation, the spread on this data set, is just over 2 years of age for the black bears.